All right, just about to start the Gen Chem stream for week 6. Hello, hello. I'm Sam. It is Friday night, just turned 8 o'clock. So let's dive in. I was actually just sort of working through some details for fun on the last problem for today. So sneak peek, if we get to the end, which we totally might, because I might go long if I need to, and preparing for this went faster than normal. So let's dive right in. Our topic for today, generally speaking, is thermodynamics, and delta G equals delta H minus T delta S. That's one of the real big important equations that we're going to use. Another one that is big and important is delta G equals negative RT times the natural log of K. We're going to use that a few times. And also, if you wanted to solve for k in the context of this equation that I just gave you, you could rearrange it and solve for k uh, in the terms of k equals e to the delta g over negative RT. So those are the three mathematical equations that we are going to use to get a lot of these answers, but not all. There's another big topic that we're also going to use, which is if you have a delta G, H, or S of a reaction, the change in the G, H, or S, and we'll talk about what all those are as we encounter them, the change in that thing will equal the sum of the change in that thing adjusted to it to the stoichiometric, that's what that is, coefficient appropriately of that same deal. And you guessed it, you know what's going on here. This is the products minus the reactants. So that's the other big thing we're going to be doing a lot, is looking at equations such as these first two. We're going to do the boiling of tin chloride and the creation of water over here. We're going to solve for the delta S of those things. Oh yeah, forgot the standards. By looking at the products minus reactants. So that's an overview. Let's dive right in. So there is a table in the back of your book. Of course, I'm going to show you in a little bit. It's Appendix G. Let me just show you right now. I have it over here. Here we go. Right here. Takes a sec to load, but there we go. This is it. And it's at the bottom here. Yeah, Appendix G in the textbook that we're using. And as you can see, the columns of Appendix G, it's the name of the thing, uh, name of the substance, grouped by element. But I just want to point out, this copied weird, but these F's here, let me zoom in even more so I can be sure you see it. So I just want to note, while we're here, delta H or enthalpy, this F is of formation, and it copied weird. And that's the change in enthalpy to make the thing. And I just want to point out, aluminum is a great example right here. Al by itself, one aluminum atom by itself as a solid, that is the native form, or maybe there's another exact vocabulary term for that, but that's aluminum's happy place. And it doesn't cost any heat per mole to get there. And it doesn't cost any free energy per mole either to get there. So I just want to note that things in their native form have 0 delta H of formation, 0 delta G of formation. But notice that over here with delta S, there is no, it's not of formation. See, there's an entry in everything. Not of formation. None of those are going to be 0 because the only way to get delta S, I believe it's the third principle of thermodynamics, or third law, is to be at absolute zero. And let's note one other thing, is that the units here on delta H are kilojoules per mole. Units of delta G, free energy, kilojoules per mole. But the units of delta S are joules per mole per Kelvin. So frequently it's a good idea to convert the joules to kilojoules right away, because if you're combining your S's with your G's and H's, you want to be in one unit. Okay, quick overview of Appendix G. I've already copied everything we need, but this is where all that information comes from. Appendix G. Also, while I'm here, let me just point out that in the textbook, there's this list of equations like the one I noted. This is the other one I noted that we're mainly going to use today. I don't believe we're going to use these other equations today, but they're good to know. So awesome. Let's actually start doing this stuff. So reaction A over here, change colors. Go for this bright purple. Reaction A, we have tin chloride as a liquid, so it's evaporating, it's boiling. Tin chloride as a liquid, and it's going to tin 4 chloride, we should say, as a gas. And we had over here, it was HGS, let's recall. And this is all about S, entropy. And the units of entropy were joules per mole Kelvin in the table. And let's just do a quick gut check. The entropy should increase. It starts as a liquid, which stays as one thing together, and it becomes a gas, which scatters all over. That's more microstates, more chaos, more disorder. So we're going to expect the entropy to increase here. And how are we going to do that? It's because the product is right here. The reactant is right here, and you'll notice when I zoom in, I apologize that I'm so zoomed out. I'm trying to make sure I'm giving you a good view of everything. A bit pixelated, but this top row is for the liquid. So the two items from the table that I grabbed are for the liquid. The bottom one's for the gas. So I grabbed the liquid and gas. And that means to solve for the delta S of this reaction, it's going to be, this one's pretty simple because there's one thing on this side and there's one thing on this side. So we don't have to sum anything or think about stoichiometry at all. All we have to do is the delta S of the product minus the delta S of the reactant. And that is, we've got product and reactant. So we've got 365. And I don't even have to convert the units on this. 365.8. I don't have to convert the units because we're just sticking in delta S land. We're not talking about anything else. And if you do that very simple subtraction thing, which I already did, so that hopefully we can get through this whole worksheet on time today, you will find the product, right, is the gas. The reactant is the liquid here. That the difference between those two things is 107.2 joules per mole Kelvin. So again, this makes sense. We have a positive delta S because entropy went up because we went from a liquid, which is relatively ordered, to a gas, which is relatively disordered. Okay, awesome. Let's do entry E, which is the formation of water right here, right? Let's just do this the quick way. So, formation of water And I already pointed out everything we need. Now, when reading a table like this, part of the reason I left these arrows here is because it's so easy to get confused if you're moving fast. You have to pay attention to the numbers and to the states and stuff, and like that looks so similar to that or that if you're moving fast. So I just want to caution you, if you happen to be in a scenario where you're looking at a table like this, just really pay meticulous attention for your own sake. So let's note once again, hydrogen and protons are in their native state, so they don't have a delta G formation. This is interesting. I actually just noticed that the delta S of a proton. I'm not going to comment on that because I don't know what's up with that. It is kind of surprising, but I guess maybe not. Protons aren't officially atoms, or are they? I don't know. They're just nucleuses. Yeah, they're atoms. I'm not going to go off on that. Let's circle back to that because that could be really interesting. Either way, it's not involved in this problem. Let's just organize these things, since we already know what we're doing here, by the delta S of this reaction. Let's just organize them now as our products. So our product is water, and now stoichiometry does come into play. We're going to get 2 waters from doing one of this whole reaction. This whole reaction runs once, we get 2 waters. And the water, here we go, liquid water. And again, this would be an easy place to mess up and grab the gaseous water one. And you'd be wrong. So we have liquid water products. That's all of our products. We're going to subtract the reactants, which we're talking delta S. So for our H2, by the way, should have put a 2 there. So let's go ahead and do that. 130.7. And oxygen, which again, here's oxygen down here. Delta H and G are 0, but there is entropy. There is chaos, even in oxygen's happy place, which is O2. So, but we only have one O2. So 1 times 205. 2. And I already did the math, and I just want to rush through this. So if you do the math on that, then, well, I'll give you one step. After you crunch that a little bit, what you end up with, that part's kind of obvious, minus 466.6 is the whole reactant part. So you can see that this is going to be negative. It's going to be negative 326, and all of that was in joules per mole Kelvin. So let's note that the delta S for this reaction, by the way, I should have been throwing those out there this whole time. We'll talk about what that means in a sec, is negative 326 joules per mole Kelvin, which means it gets less chaotic when this reaction happens, which again makes sense. Look, on the left side, we have 3 total moles of gas. That's a pretty gassy side. The reactant side is pretty gassy. On the right side, we have 2 moles of liquid. So if we were comparing liquid to solid, it might be a different story, but when we're comparing liquid to gas, this is reactants. This is much more ordered. Less entropy, less or fewer microstates. The delta S has gone down there, and that makes sense. So we like that. Okay, there's the first two. So the next question we're going to look at asks us to determine the entropy change for the combustion of propane. And this is basically the same problem that we just did, except for you have to know what combustion is and do a little bit of extra work balancing the chemical equation. So combustion of anything, you have your CH something or another. There's some numbers going on here. Let's not talk about the details there. And you add it to oxygen, some number of oxygen, and it becomes carbon dioxide and water. And that's very ambiguous that I meant just some number of oxygen. So let's just say that this is the basic form of combustion. When we say combustion in chemistry, it has a specific definition, and it's that you have a hydrocarbon and you have molecular oxygen gas, and this is a gas too, and it becomes CO2 gas and it becomes H2O gas. So water vapor and carbon dioxide. Oh, and of course, the whole reason we do combustion is because it generates a ton of heat, which you could harness to do work if you wanted. So that's why we do it. Chemically, what we're looking at is this part. Although, I mean, it's really not a bad idea to talk about heat. This is thermochemistry, or I guess it's thermodynamics. So anyhow, let's write this out for our specific scenario where we have propane as our hydrocarbon. And now it's definitely fair to leave some space because there's going to be some number of oxygen molecules that are going to react with propane into spark or some sort of catalyst. Or maybe it's spontaneous combustion. And then we're going to get some amount of CO2 and some amount of water. So after we do this step, when we set up this kind of thing, our delta S products minus reactants, we're going to have a lot going on with our stoichiometric coefficients. That's kind of the point of this problem, in my opinion. So the thing now, of course, is we have 3 carbons on this side. There's only 1 carbon there, so we need at least 3 CO2s. So concurrently, let's just note that we've got 8 hydrogens on this side. There's only 2 hydrogens right here, so we're going to need at least 4 H2Os. I just balanced the C's and the H's, but now we have way more oxygens on the right side than we have on the left side. So let's look right here really quick. We have 6 oxygens right there, and here we have 4. And so that's 10 total. So how do we make this 10 oxygens? Here's a mistake I personally make way too often. Don't make it yourself. This is O2, remember. Way too many times have I been lazy and put a 10 there. No, it's O2. You have to divide the 10 because there's 2 of them for every one that we write in the stoichiometric coefficient spot. So now that we've done the balanced chemical equation, the rest of this should be a breeze. So, think about this for a sec if you forgot how to balance chemical equations. Hopefully that made sense. Sometimes when you do combustion, depending on what you're starting with, you might end up with some weird fraction of oxygens, and then it's up to you if you want to multiply everything by 2 or just leave oxygen as a weird fraction. But this one was convenient because we got only integers for stoichiometric coefficients. And by the way, again, I was lazy earlier. That little symbol means standard, which means that we are at 298.15 degrees Kelvin, which of course is the same thing as 25 degrees Celsius, and we're at 1 atmosphere of pressure. I don't think that is even going to be a concern. I shouldn't have crossed it out because it's true. But we do have to keep this in mind sometimes, and I just think it's important. I should have clarified that everything that I've been talking about so far, and all of the delta H enthalpy, delta G free energy, and delta S entropy depend on the temperature. So if it's not at standard temperature, you would have to say that this is at 5,000 Kelvin or something, or this is at 10 Kelvin. You would have to say that, but instead of bothering to say that, and since people like to do experiments in normal rooms at room temperature and sea level, we just like to keep track of everything from here. So I just wanted to clarify that. I should have mentioned that earlier. And the standard delta S of our reaction is going to equal our products with their coefficients. So let me get this right this time. We got our products, which is going to be 3 times, I obviously did not leave enough space. Oh. Looks like the delta S of CO2. And again, let's be careful. What if they gave us the liquid one too? They probably did. What if you accidentally got the CO2 liquid value that was right under on the table? You'd be wrong. So just be so careful. I've made this mistake so many times too, the one I'm warning you about. So just be careful about that. we are going to get 213.8. And again, this is going to be joules per mole Kelvin. Whereas this is kilojoules per mole. This is kilojoules per mole. Just remember that as well. And we're adding all the products together. So this was the one for CO2, the one for water right here, right? Water, gaseous water, that's a good example. The one for liquid water was right below it. I made sure to grab gaseous water because that is what combustion is. And that is corroborated, by the way, because they say gaseous, carbon dioxide, and water. So if anyone thinks I misinterpreted that and it should be liquid water, you might be right. I'm just explaining my rationale. Also because, let's not forget, when combustion happens, it's hot. And I'm pretty sure I looked it up earlier, but that's what I'm rolling with, by the way. If I'm wrong about that, then do everything I'm doing here and just switch in the value for liquid water. And you'll get a different number, but the principle will stand. So 188.8. So that was our products. Gaseous water, gaseous CO2. And we're going to subtract from that the reactants. And again, we had to do that stoichiometry first. Here we are for propane, gaseous propane, it's 270. We had to do the stoichiometry first to know what to put into these spots. And we're going to add that to 5. For oxygen, it's 205.2. And obviously, be careful. This is quite easy math, but also easy to mess up math because look how many parentheses I'm using, right? Let me also write that that's reactants. Parentheses are free. Just keep things clear. Not just for you, but for your calculator. Your calculator is notorious for messing up parentheses. So it looks like when you do all that math, I hope you get this, because this is what I got. If you get something different, then one of us was wrong. And it very well might be me, but I practiced that earlier. I think I did that math right, and in the interest of hitting all these problems, I'm not going to do it again. But it seems plausible. Let's gut check. Does it make sense? Do we have more chaos? Let's see if it makes sense. We have 1 gas molecule and 5 gas molecules. So we have 6 gas moles, molecules or moles. I should really say 6 moles of gas molecules. That's pretty accurate. And over here we have 7. So if you could control this and make sure that that was liquid water, then the entropy would probably go down. But since I assumed that the water would be gaseous because we're combusting and it's really hot. Although then again, now I am questioning myself because if we're doing this, now I'm going to roll with that. It might be 25 degrees outside, but it's hotter than that in the engine. So that is our delta S. The big important part of that is we had to do a bunch of stoichiometry first so that we knew what to plug in there, there, there. Get that answer. So let's move on to the next one. I think we're now going to start going into our delta H, and we're going to find if stuff is spontaneous at 500 or 700. What does stuff mean? Let's actually talk about this. This is actually really cool. Table salt, right? Sodium chloride. And right now on your table, that sodium chloride is in there in little chunks that are solid, right? Salt. And so we can definitely say that at room temperature, that stuff has not melted. But we are talking about the reaction in which that solid stuff becomes the liquid stuff. So melting salt, and we're not talking about dissolving salt, because dissolving is when it breaks up into its pieces. So this isn't that it's breaking up into its pieces. They're staying in an ionic bond. It's a phase change of the sample becoming liquid. So we're going to expect, by the way, that the delta S is going to go up here. Oh, that's not the question, but it's true. Look, here it is as a solid, here it is as a liquid. That's higher. So it does. We actually are solving for spontaneity, right? So it might seem daunting to consider how you would do that because you have to know this detail. I don't know why that thing won't go away. I guess it probably will later. The detail is this. There's kind of two ways to look at spontaneity. Spontaneity in the context of the variables we've given. One is the delta G way, and one is the K way. And they're super related because we had that equation that related delta G and K. But one definition of delta G, which is Gibbs, that's the G part, free energy is the definition part, and that is how much energy does this system have just sitting around that could be doing something. And it's a bit of an esoteric concept. It's typically measured in kilojoules per mole. Could be joules per mole, could be any energy unit per mole. But kilojoules per mole is the convention. And if delta G is negative, that means that the chemical system, the reaction that you're talking about, will lose, oops, let me not write loose, it will lose energy, and that makes it happy. Chemical systems don't like having a bunch of frenetic nervous energy. It's annoying, you know, to personify chemicals. They like to lose energy. They want to chill out. If they have an opportunity to chill out and get rid of their free energy, they will. So if you have a negative delta G, then the system or reaction will lose energy, and that makes the system happy. And so a negative delta G is just going to happen. It's spontaneous. If you have a negative delta G, then this reaction is going to be happier after it happens. So negative delta G makes the reaction spontaneous. The very much related other way to look at it is that if your reaction is at equilibrium, then its mass action expression, which is Q, is going to be referred to as K, right? And we can look at reactions in terms of K as a solubility product, K as an acid dissociation, K as a base dissociation, K as gas pressures, K as concentrations of something I haven't covered yet. There's lots of slight variations on K, but fundamentally, K is a special kind of Q where you have your products, but in this case, that's a concentration, right? That's in terms of moles per liter specifically, which is molar, right? That unit. This has to be that unit. Just keep that in mind. If you're going to calculate a K that comports with the conventions that we use. And the other thing to keep in mind is that product X is going to be raised to its product Y is going to be raised to its stoichiometric coefficient if our reaction was AAs plus BBs leads to, but also reversible with X X's and Y Y's. That's what I'm writing out here. This is our expression, and you probably know all this, but it's good to just think about it again and tie it all together. So here's the concentration of reactants A to its coefficient, reactant B to its coefficient. So if we're at equilibrium, if it's going back and forth at the same rate and it stops changing when you look at it over time, then K is the same thing as Q. So that's if you're at equilibrium. But Q is when you're not at equilibrium. And if your Q is less than your K, then that means that you have too little product. And it should be spontaneous. It's going to go forward the way you wrote it and get more product. So it should happen. But if your Q is bigger than K, you already have too much product. So if anything, the reverse will be spontaneous. But it's always important to remember that even though it's reversible, we wrote it this way. We called these the reactants. The way we wrote it, if we wanted to write it the other way, we could. It's a reversible reaction. But we called those the reactants, so we kind of stick with it, right? And we call those the products. So if the Q at any given time, it's not at equilibrium, it's at any given time that isn't equilibrium. If the Q is less than the K, then it's going to go forward and happen. It's going to be spontaneous because the products need to go up. If it's less than it, it needs more products. If the Q is greater than the K, you have too much product and it's going to go the other direction. Okay, probably an over explanation, but maybe it was just what somebody needed out there. So now that we've covered that, let's look at how we're going to solve for either delta G or K, right? Because they didn't give us that. They only gave us an H and an S and another S. And we just did a bunch of problems on what to do with multiple S's. The S of the reaction, standard delta S of the reaction, is just going to be the product, which is the liquid, because we're talking about melting. And the delta S of the product is that many joules per mole Kelvin. We're going to subtract from the product the reactant, which is 72. And then, since those are the same units, I'm just putting the units on the outside. And so the delta S for this reaction is going to equal, I feel like I should do that in my head, but since I already just blabbed on for way too long, I'm just going to look, is 22.95 joules per mole Kelvin. Now, in just a sec, we're going to see why we want to just start thinking about this in terms of kilojoules right away. Because the route we're going to go, since we have that, and we were given that delta H equals 27.95 kilojoules per mole, we could convert either one of these into the other, or sorry, either one of these units into the other. But I'm going to convert this up because our delta G, usually we're looking for kilojoules anyway. So that's the way I'm going to trend. So speaking of delta G, remember that our delta G is going to equal our delta H minus our temperature in Kelvin times delta S. And we've already foreshadowed how we're going to know if this is spontaneous or not. And if it's spontaneous, it will melt, and if it's not, it won't. We'll know if it's spontaneous or not from this route, where if we have a negative delta G, it's spontaneous. If we have a positive delta G, that means the system would gain nervous energy, and it doesn't want to happen. So we just have to solve for delta G, and now it should be easy because we already did this preliminary reaction for delta S. So delta G at standard conditions of our reaction is going to equal the given delta H in standard conditions, which is, sorry, 27.95 kilojoules per mole. And we're going to subtract the temperature, which this is part of the question, right? So is it spontaneous at 500 C and 700 C? Now, of course, to convert from C to K, which you have to do, because look, our our entropy value, or delta S over here, is in moles kelvins, joules per moles Kelvin. So we have to be in Kelvin to use it. So our Celsius plus 273.15, and plenty of people skip the 0.15, but I figure if you're going to be sciencey, be sciencey. So there we go. So that's our first temperature point in Kelvin. The other one was 700 degrees Celsius, 273.15, and that is obviously going to equal that. So let's solve it for the first one first. And times the delta S that we found, but we have to convert it from 22.95 joules per mole. We have to convert that to kilojoules per mole. So if the decimal place would have started here, that we have to move it over 3. So there's where it originally starts. Let's move it once, twice, thrice, and we need to fill in that 0, add a 0 across the real decimal place, get rid of. So I'm just going to take that for granted, but that's what I do when I do this kind of thing usually. So now we've converted to kilojoules per mole Kelvin. Oh, and that's Kelvin. Should have written that, of course. So this is great because here we have kilojoules per mole. Here our kelvins cancel out, and now we have kilojoules per mole. So this now makes sense. If these aren't the same unit, you can't do any math on it. But if they are the same unit, then we have 27.95 kilojoules per mole minus 17.744. And, you know, I did these calculations a few hours ago, so please, if you are calculating along and you find an error, submit a comment or something. I'll see if I can fix it or something. Or just cut me some slack. I'm only human. Okay, so there we go. That is our delta G. And it equals not negative. So at 500 degrees Celsius, sodium chloride, solid sodium chloride, does not melt. You can't melt your table salt. If you go and turn the heat up on your thermostat to 500 degrees Celsius, you still won't melt your table salt. Obviously, you shouldn't do that, and I'm reasonably sure you couldn't do that, because that'd be insane if they designed a thermostat for somebody's house that went up that high. So let's do this exact same thing. That was at 500 degrees Celsius, which was this Kelvin, right? Let's see for 700 degrees Celsius, the delta G. And now this is kind of an interesting thing to think about, by the way, because this delta G standard is supposed to be for 273.15 degrees Kelvin. This is actually part of the assumption we're making. I think we're asked to talk about in a sec. But like we're saying that we're not doing it at that. So we kind of have to assume that there's not going to be a huge difference in this temperature range, which may or may not be the case. Like imagine if we were calculating this for 70,000 degrees, then it would be pretty far-fetched to think that the characteristics of various thermodynamic properties at 70,000 versus 273, it'd be pretty far-fetched to think that those would be similar. But when we're within the hundreds, yeah, maybe. Anyway, that's the assumption we're making as we do this. So the only thing we're changing from when we did that previous equation is the temperature that we're inputting. So minus, remember, it's 200 degrees hotter. Same delta S, which is what I'm writing in there right now. How's that? That was T, H, G, right? And I already converted it. Kelvin, Kelvin. And you math that on out, and you get is obviously going to be spontaneous now, right? No, it's not. Oh, psych. Gotcha. It's still positive. Less positive. You're closer. You're much closer. But, so even at 700 degrees Celsius, it doesn't melt. The melting is not spontaneous. Spontaneous means does it happen or not, basically. Now, if you contributed 5.6 extra kilojoules per mole of salt, then you can make it happen, right? So spontaneous means it happens on its own. Even if it's only a balmy 500 degrees Celsius in your living room, it would still cost you 10.21 kilojoules per mole of salt to melt it. So you still could make it melt, but you have to give it more and more energy. You have to add energy. You have to add free energy. It doesn't get to lose any. So at what should we solve for the temperature it does melt at? I guess let's do it. So if delta G were 0, so this is, by the way, would be equilibrium. This is when Q equals K. It doesn't go forward or backwards. Your delta G equals 0. And if your delta G equals 0, then we would have this minus some temperature that we don't know. That's what we're solving for. This is like a side quest on the actual question. It's in Kelvin, though, but Kelvin, Kelvin, kaboom, kabang. And so that means that we could say that I'm going to bring the left over to the right. 2295 equals 27, times T. Let me do that a little bit more good looking like. So we've got that delta S thing that we figured out earlier with the kilojoules version. That times this temperature at the Kelvin, Kelvin, we'll cancel that later, equals 27.95. So now I obviously just divide both sides. That means our temperature is going to equal 27.95. By the way, this is our kilojoules per mole. That's the delta H. And it was kilojoules per mole. So divided by our delta S. So by the way, I guess next time I do this, we're just going to say that T equals delta H over delta S if delta G is 0. That's a crucial part. That's only necessarily true if delta G is 0, but if it is, then they're all standard. Then the temperature at which delta G is 0 is this. I guess if delta G was something else, you could solve accordingly, but you'd have to do other math first. But it's very simple this way. So delta S in kilojoules was this, kilojoules per mole Kelvin. And since this Kelvin right here is on the bottom of a thing that's on the bottom, right, double bottom, it flips up top, which is why we end up with the units on top for the answer. And I did not do this earlier, actually, so let's do that really quick. 27.95 divided by 0.2295 equals, using the old calculadora, 1,217.86 Kelvin. Is the temperature equals delta G equals 0, or right, temperature. This temperature is when delta G equals 0. So if we went up one teensy bit above it, that would be the melting point of salt. So for the sig figs that I'm expressing here, let's just say that we went here. We take it up one teeny thing above delta G and hold it there. We continue to hold it there. Then your salt should melt. That would have a delta G equals slightly negative. And from there up, it should melt. Now that's Kelvin. So to get that back, 1217 to get that back into Celsius. We would just do this. So we got a 2 and a 7 and a 4. And you go away and become, because you, well, first you become that, that becomes that, that becomes that. That goes over here. And now we have 11 minus 2. Is that right? 900. Yeah, so I just calculated that. Let me just think about that for a sec. That looks wrong. I messed that up. I'm going to use a calculator. I'm holding one right here. I apologize for wasting your time trying to mess up arithmetic. No, I got it right. Cool. I statted myself. It's just also different than what I had read on the internet earlier, but that's fine. It expresses the general range. So 944, based on what I just did, 944 degrees Celsius, approximately 945, let's call it, because then we're definitely high enough, will melt table salt. So that's how hot you would have to make your apartment if you wanted to melt table salt. Okay, that was fun. Let's keep going. This next one should be pretty quick. And we already talked about it. Delta G and delta G with the standard symbol. This is delta G in any condition. It could be 5 degrees Kelvin. It could be 5,000 degrees Kelvin. Also, pressure could be, you know, 0.0001 atmosphere, or, sorry, lowercase, or, Samuel. It could be anything. That's delta G. Delta G standard is specifically 298.15 Kelvin and 1 atmosphere, or whatever equivalent you want to use for pressure. But that is the international unit. So I hope I'm not missing anything. The one thing, I guess, is this that's important to note. If you want to find the delta G in any conditions, and you have enough information, you could calculate it, and then you'll know if your reaction will happen. And what you need to know to do that is your delta G standard, and you're going to add R, which is the gas constant, the temperature in Kelvin, whatever that is, times the natural log of the Q that we talked about it earlier, the reaction quotient. And for this worksheet, what that means, if your delta G is at equilibrium, then your delta G is 0, as we just talked about up there, the salt thing. If you're at equilibrium, let me just clarify that now we're talking about this. If you're at equilibrium, then your Q is K, as we mentioned earlier. That's the definition of K. So this allows us to actually solve for our delta G standard at equilibrium. Because what we're going to do is subtract this whole little chunk in green. We're going to subtract it from both sides. And I'm also just going to flip the sides around. So our standard delta G, therefore, is negative RT ln K, which is one of those equations I wrote at the very beginning of this. Okay, so that's, I think, a probably way too thorough answer for this. And I guess it's getting dark. Let me turn on the light. Add some lights. Here we go. Here we go. Cool. So what's going on here? So this is some more of what we were talking about earlier. I just wanted to note this is pretty interesting. Once again, like solid copper, it's totally happy just being a single copper atom by itself, so it doesn't cost you any heat or any energy. That's our enthalpy, which is basically heat. It's just heat per mole. And that's our non-heat free energy. It doesn't cost anything to make copper just be itself, but it does cost something to make copper bind with sulfur. It doesn't like that as much. Although actually, I retract that. It doesn't cost anything. It does that for fun. It loves it. So I picked a bad example there. But here's a good example. Sulfur is really interesting because its favorite way to be is in a group of 8, which, did I do that? Yeah, something like that. I don't know how the shape goes. It's some sort of little geometric prism or something of 8. Isn't that cool? That is sulfur's favorite way to be. It's a solid molecule of 8 sulfur atoms, and so it has a 0 delta H and delta G. But if you force sulfur to be a gas, that's when it costs you a lot. So that would have been a much better example. Copper actually is totally fine becoming copper sulfide, so that was actually a really silly example. But I think it's interesting to point out. So let's look at this first reaction. We can use this data from the table. Of course, as always, kilojoules per mole, and joules per mole Kelvin. So we're identifying as either spontaneous or non-spontaneous, right? So that means that we are looking for some delta G info. And how we're going to do that is similar to when we were doing with delta S, but we're going to do that whole delta, the sum of the delta G's of the products with stoichiometric coefficients as appropriate minus that of the reactants is going to be how we get the delta G of the whole reaction. And that could apply to delta H as well. So the free energy of the products minus the reactants. That's what we are going for here. So our product is our copper sulfide. So our delta G for our first one, for our formation of copper sulfide, our product, our delta G, is negative 53.6 kilojoules per mole. And again, that was our product. And our reactants, we have 2 of them. And the delta G for this one, well, it's solid copper. The delta G is 0. That's 2 times 0, which I'm just going to write to be unnecessarily thorough. And so that was for the copper, right? This is the copper sulfide. And within the reactants, we also have gaseous sulfur. So let's note again, sulfur would have preferred to be in a solid chunk with 7 of its friends in a group of 8, but we force it to be a gas, and doing so costs that much energy per mole. 200, oops, let me write that not incorrectly. It cost 238.25 kilojoules per mole. And when you do that math, sorry, that shouldn't be an arrow, that should be an equals. When you do that math, your delta G of your reaction is going to equal negative 291.5 kilojoules per mole. So that's spontaneous. So that means if you expose solid copper to gaseous sulfur, you will create solid cupric sulfide. That's got to be called, or copper 1 sulfide. Even though there's 2 coppers, the charge on it is 1, and you know that sulfur's minus 1. So anyway, that's a deal there. Okay, so, and that also means I wrote it incorrectly here. There we go, copper 2 sulfide. The next one they're asking about is a little bit more complicated. We've got this, this, and this. Oh, nice. I already copied it down here for us. So first, just for fun, let's note that an O by itself is going to be an O2 minus, because it will have gained 2 extra electrons, right? Because O is typically like that, but if it's forced to hang out on its own, it's got to steal some electrons from somebody, so we've got 2 extra. So if we've got 3 of those, that equals 6 minus equals the charge, Z is the symbol for that, equals the, charge on the oxygens, just the O's that are inside this O3. So that means that the iron needs to be +6, and since there's two of them, that means each one is iron 3. Iron 3 plus 3 O2 minuses. That's like the ionic composition of the solid. So we would call this iron 3 oxide. So just a fun side quest and a reminder for how to talk about this kind of stuff. And you would need to know that if you were dissolving this. In this case, we're not dissolving it. It looks like we're reducing it. Yeah, we're reducing it with carbon monoxide. Very interesting. But we're going to do the same deal as before. The one thing is we got to be super careful. Solid gas, because we're going to have, I'm sure, some tempting distractions for marking these wrong in here. Yeah, just be real careful about these numbers. It'd be so easy to get confused. But Fe2O3 is the one we're looking for. G was in the middle. So that's this, 742.2. So, oh yeah, and that's reactant. So actually, our delta G for our iron by itself is 0. Carbon dioxide is 394.36. So we're going to have that our delta G of our reaction is going to equal, we have 3 carbon dioxides, and that was at negative 394.36. That's pretty low, so that's good. Good sign. We're going to add that, since it's still our products, to the delta G for iron, which is 2 times 0. So that's convenient. Makes the math a lot easier. That was all kilojoules per mole. And this whole thing's kilojoules per mole. So that's our products. And then our reactants, I'm just going to do this one vertically. We're going to subtract. And reactant-wise, we have only 1 times our Fe2O3 solid, which is negative 742.2. And we're adding that to our carbon monoxide right here, which we have 3 of. And that's the same unit. And you do all that math, multiply some things, add them together, subtract them from each other, and it looks like we get, for this next one, that our delta G, our reaction, is negative 29.43. So again, spontaneous. Not as much as the last one, where we just had negative 291. So it's a tenth. You're probably going to get like a tenth as much results, so to speak, but it's still going to happen. So, okay, great. Let's keep rolling. We have a few minutes left, and yeah, I might go a few minutes over so we can get through all of these problems. Looking for my cat. Oh, he's right there. He's been behind me this whole time. So, I'll show you my cat at the end of the video. Diego has to make an appearance. He's just sleeping right now. Just getting his beauty rest. So this is an ideal place. Sorry, this definitely scanned really weird looking. When I say scanned, I mean like screenshotted. So I apologize for the sort of pixelated appearance there, but this is the case where we're going to calculate the delta G based on the fact that we've been given a T, we've been given a K. In this case, it's Kp, so it's in terms of pressures, but it's still products of reactants. It's still the same thing as any other K in that sense. And we've been given it, so we don't actually have to do any work there. All we have to do is solve this little deal. So we're looking for delta G standard, and as we discussed a few minutes ago, if you rearrange that other equation for when you're at equilibrium, that is how you solve for delta G. The one thing to be careful about is that R has many identities based on the units you're using, and this is probably the most common one. Another one that you might know, uses different units, but still the same thing. Liter atmospheres per mole Kelvin. Those are both versions of R. And there's other ones that use bars and that use pascals and this, that, the other thing. But the one that you want to use, since delta G is going to be, or usually is, conventionally is kilojoules per mole, you want to use the R, the gas constant, that is this, but converted to kilojoules. So we move that decimal over 3 places. So just make sure that you use that R for these. And you're going to see in a sec, there's another number that you can use to make things way simpler. Oh, Diego just left, so I don't know if we're going to have a... Oh, it just turned 9. So he must be like, hey, I waited this entire hour. See if I can get him, if I can coax him back. I'm going to at least finish this problem. Diego. We'll see if he comes back. Okay. So this first one should be really easy to solve because delta G equals negative the R that I just talked about. Since I now converted it to kilojoules. And then we're multiplying that by, well, looks like 980 degrees Celsius. And again, we're making that same assumption that the fact that temperature is not actually the one we talked about, like I guess, yeah, that's kind of a paradox that confused me a little bit. But let's just roll through it because this is how you do these problems. So this temperature 900 degrees Celsius, let's not forget to Kelvin it. That's plus 273, so that makes it 1173.15 Kelvin. And that is going to be times the natural log of the K that they give us, right? Because that was the Celsius. Here's the K they just gave us, which is 1.04. And I presume I did that math. Here, let me find it. Was I reading? Oh, you know, when I did this before, I now realize I read the wrong entry on there. That's fine. It's only going to take a sec. I just have to calculate again. Yeah, I just read the correct one with this 1.04. When I did this before, I accidentally just took the top value, but that's for a different reaction. So, oops, on the previous time I did it. Oh, I just did it wrong again. My darn bad. I read them both wrong. Okay, I apologize. I'm 80 short over here. I caught my mistakes, but I also made them. I added that to 900, but I should have added it to 80, so it's going to be a 5. Yeah, there we go. 1253. That right? And I messed up that number when I did this before. Again, this is fine. I'll just do it correctly this time. Okay, plus the correct KP here is, those are not negatives, that's just a dash, right? Yeah. So 1.67, the natural log of 1.67. All right, sorry for anyone who just sat through that. I had just read that table. I just like mixed my lines up. But luckily I noticed it that time. So let's multiply out these first two terms. And then, so let's start with this. The natural log of 1.67 is 0.513. And these first two terms, 0.00083145 times 1253.15, 10.42. Negative. I always forget that. Not always, but frequently. So be careful about that. Negative 10.4193, etc. times the natural log of 1.67, which is 0.513, equals negative 5.34, which was the delta G. So this is spontaneous. And they weren't asking us that, but I just instinctively answer that. Anyway, it is spontaneous. And that is the delta G for that reaction. So, okay, so it's 9:04. We have one more problem in this. Let me just see how many more problems we have. We have one there, and we have 2, 3, 4, 5. Oh, and this is the one I had started working on. So I think what I'm going to do for this video is just this second problem on the one I'm on right now, and I'm going to call it a night and hopefully make a video where I go through the problems I didn't get to today. So let's just do this one last one. So I'll do this one over here to the side. Do it in a different color to just set it apart. Go back to my classic orange. So for E, we have that the delta G is going to equal negative RT ln K, and that's going to equal negative 0.008345 times, in this case, our temperature is 25 degrees Celsius, so that's 298. So now this makes sense because this actually is at standard temperature. That's Kelvin. This was kilojoules per mole Kelvin, so our Kelvins just canceled. And now we're multiplying this by the natural log of the given K, which is 7.2 times 10 to the minus 4. Okay, so 0.008 times 298.15 was that 2.48. Got negative 2.48 basically. So that's a good one to remember because this particular RT is very common for these problems. So a good thing to sort of just memorize approximately right there, that negative 2.48 kilojoules per mole is RT at 25 degrees Celsius. And the natural log of 7.2 times 10 to the minus fourth, oops, sorry, quit that. Natural log of 7.2 times 10 to the minus 4 is negative 7. Oh, I just noticed that I'm writing where my head is. So I don't think I've done that earlier in the video, but if you're still watching, let me move this for you. Okay, so minus, if you solve for the natural log of 7.2, by which I mean you put it in your calculator and it solves it for you, 7.2, that was 7.2 times 10 to the minus 4, just to make it clear. 36. And if you multiply those together, pardon me, then I think you might see where this is going. So because they're both negative, when we multiply them together, we get a positive number. We get positive 17. This is not spontaneous. They didn't ask us that. They just asked us to solve for it, but we know now to just think about that. And that is the delta G of that based on the given information. So again, in this case, we solved for delta G and therefore spontaneity using that equation. Whereas earlier in this worksheet, we kind of did the same thing there. But earlier in this worksheet, we solved for delta G with this equation. And they're both, and you could set those equations equal. You could combine those equations if you needed to for whatever algebraic purposes. So I just want to point out that, once again, those are the two main things that we worked with. If we had made it to the end of the sheet, we would have done that as well. But we did a lot of this, right? The sum of the G, H, or S equals the products G, H, or S, sum of those. Sorry. the singular G delta H delta S of the reaction equals the sum of the products minus the sum of the reactants. So that was a big thing we used, and then we used this for a few, and then we used this for a few. So awesome. I hope you have a good day, night, evening, weekend, weekday, spring, winter, fall, whenever you're watching this. Summer too. That's what we're having. We're about to get there. And yeah, we'll see you in the next one. And hopefully soon I will post a few more problems along these lines if you need. Have a good one. I need like a better call out. Oh, my cat's not here, so this is the first one with no Diego, but so be it. Okay, see ya.